Fitness trackers count steps towards your daily goal, and you might also use them to map your route. As you travel along the trail, a small electronic receiver sends timing information back and forth to satellites in orbit 20,000 kilometers above you. This information is used to pinpoint your location and how you move along with meter accuracy. But a runner's course is not the only thing that global navigation satellite systems can trace. They can also track complex geological processes, like the ones that cause Memorial Stadium to slowly drift over time. As mentioned in a previous video, Earth's tectonic plates are in motion, just on a much finer scale. Like a fitness tracker for the ground, fixed GPS monuments record how the ground moves both slowly over many years or quickly during an earthquake. Real-time measurements of how the ground moves or deforms during large earthquakes allow scientists to estimate the size and extent of the fault rupture within tens of seconds. Knowing the orientation and magnitude of the slip for large faults provides information useful for rapid hazard assessment, particularly for local tsunami warnings. Let's head back to the Berkeley Seismology Lab to meet Dr. Christine Ruhl, who can explain how we use a program called G-LARMS to merge GPS and earthquake science.
GPS instruments quickly and accurately measure how far they've moved during an earthquake. This change in position from before and after an earthquake is called the displacement or static offset. G-LARMS, which stands for the Geodetic Alarm System, is part of the Shakeler Earthquake Early Warning System, which uses these GPS displacements.
When G-LARMS is triggered by the Shakeler seismic algorithm, it uses 1 Hz GPS time series data from each GPS station to measure the static offset at that station. We then use those offsets in a mathematical inversion to figure out the slip on the fault that might have caused those offsets. You can see here that G-LARMS builds the fault with 10-kilometer patches as more GPS data comes in, solving for the amount that each section of the fault has slipped and adding more patches to best fit the data. G-LARMS tries to fit or match the static offsets and adjusts the model as needed to obtain the best fit between the observed data and the data produced by the model. Because real-time GPS noise from the atmosphere and other effects is approximately equivalent to the offsets we observe from a magnitude 6 earthquake, geodetic earthquake early warning algorithms are most useful for events larger than 6. Because large earthquakes are rare, however, we are creating a catalog of GPS waveforms for computer-simulated synthetic ruptures. In other words, we are creating fake earthquakes or fake quakes on real faults in California and Cascadia in order to test and improve G-LARMS. The fake quakes are proving useful not only to assess our G-LARMS algorithm, but can also be used to test tsunami early warning approaches. G-LARMS is but one of many approaches to earthquake early warning that uses GPS to measure the finite fault. As researchers try to improve these algorithms and attempt to mitigate hazards from ground shaking and tsunamis, GPS will continue to play a vital role in accurately and rapidly measuring the largest earthquakes.